Hello everyone. In this session we are going to start with module number 5 titled Consolidation. A very interesting and an important chapter or module you can say. We'll straight away go and then see what is there in that. Module 5 consists of all these points: consolidation of soil, definition or introduction you can say. Then there is a mass spring analogy that I'm going to do a bit later in the next video. But before that, we'll be covering in this session Terzigi's one-dimensional consolidation theory, assumptions involved, and then what are the limitations. Then governing differential equation and solution. There is no derivation, there is no mathematics involved in that. But what is the equation, what are the parameters which are involved in that, and then how those variables or parameters are dependent on one another, what they tell about the behavior of the soil. That is what we are going to study, right? That is the plan for this particular session. Okay, the other things like consolidation characteristics, laboratory, etc. will be covering in later stage. Okay, go. So when the structure is placed on a foundation consisting of soil, the loads from the structure cause the soil to be stressed. The two most important requirements for the stability of the stability and safety of the structure are will be listing them, but here you can just see structure means it may be a small structure like residential building, or it can be a huge structure like a silos, right, having filled with material, right. It will be put on the ground, maybe some kind of a deep foundation like piles or well foundation, or a variety of foundations are there. But anyway, the load of the structure or whatever you build has to go onto the soil, right? So what we should worry about is the two most important requirements for stability and safety. There are two terms, stability and safety of the structure are. So we'll see what is that which depicts stability, what is that which depicts safety. Okay, the first one is the deformation, especially the vertical deformation, which is called as a settlement. All right, settlement of the soil should not be excessive and must be within tolerable or permissible limits. So when the structure settles, if the building settles, if the whole structure settles as it is down, right, maybe a meter or so, what happens is the building which was at the ground level, now it is below by 3 feet or 1 meter, right? Hardly there will be any difference. But if part of the building settles, then there will be a problem. So that is what the point is. Now the settlement, right, how much is that? Is it within the limits, within the tolerable limits, permissible limits, or not? This is the point of concern, right? So stability depends upon character like settlement. Now what is the next point is the shear strength of the foundation of soil should be adequate to withstand the stresses induced. In the sense, safety is involved here. You put the load and then maybe it suddenly fails in the sense there will be a disaster, or the structure itself falls off. In the first case, it is not happening yet. The only thing is the structure is getting down, right? The structure is getting down is different, and the structure falls off is a different thing. So if it settles down within permissible limit, it's fine. But maybe it is not settling, but suddenly it collapses. Then it is not so good, right? So that's why the two factors which we should worry about is, if at all there is a settlement, how much is that, and then whether it is going to withstand the load that is coming on the foundation itself. There are two factors which one tells about the stability, another one tells about the safety, and then while designing the foundation you have to take care of both of these things. In the sense, the design foundation by civil engineer should not fail, that is the first criteria, and then it is not failing but it is getting settled or going down, and then how much it is going down, right? How long it is going down. So both of these things matter a lot in the design of foundation. So first of these requirements needs consideration and study of the aspect of compressibility and consolidation of the soils. Means settling means what? It is not going down, but the soil below this is getting compressed. Means if I try to show, suppose this is a building and then this is the ground level, right? So there is a layer of soil on which the foundation is laid. Now this structure is going down, in the sense the whole of this material is not going down, right? Somewhere there will be incompressible layer. Now this layer of soil is getting compressed, right? So whatever maybe around 5 meter or 6 meter or 2 meter layer of soil is there, because of the heavy load of the structure, this is getting squeezed or compressed, right? That is what is known as where that consolidation comes into picture, is this particular point, right? Compressibility and consolidation of the soils. And the second needs consideration of the aspects of shear strength and bearing capacity of the soil. So this bearing capacity, anyway, you are going to learn the geotechnical part 2, that is applied geotechnical engineering, right? But anyway, that gives you safe bearing capacity. It means how much is the load or the stress that can be carried by the soil. This is safety point of view. But stability point of view means, if it is going down, how much it goes down, in how much time it goes down, and then whether it is within the permissible limit. These are the things which are of concern. Okay, now let us see. In this particular picture I have saturated fine-grained soil. Fine-grained in the sense we are talking about the clay. We are not talking about the sand, because when the load comes on sandy soil, right, the settlement or whatever that has to happen, it happens quickly, because if the particles are big enough, right, when the load comes, the water goes out quickly, and then whatever settlement that has to happen will happen quickly. But if it is a fine-grained soil, when the load comes, the time taken by the water to go out will be large. So it may be taking, maybe in terms of days or weeks, or even in terms of years. So that is what the point of concern here. Now let us say this is fine-grained soils, in the sense clayey soil, and then it is saturated, right? Means here we have not depicted that way, but you can assume that there are soil particles, and then in between soil particles all the voids are completely filled up with water. I repeat, soil particles and then the white spaces are completely filled up with water. It is fully saturated. Okay. Now what happens is, let us say the building comes onto the structure, right? The structure or a building, when it comes, obviously it will be putting load, means there will be some pressure which will be acting onto this. So what do you expect to happen? There are voids in which the water is there are soil particles. When you put the load, obviously there will be some kind of squeezing action. So what can happen is, obviously the water which is fluid will be trying to go down, go out, right? So the water which is there will be going out, right, because of the external pressure, because of the structure. So the water goes out. The rate at which the water goes out depends upon permeability, right? Now, because it is a fine grained soils, because of that the permeability is quite less, and then it is taking a lot of time. I told you just now, it may be taking months or years. So at that rate water goes down, goes out. When water goes out, the volume of the soil reduces, or this soil gets compressed under this load. The level which was there at this, now it may come down. So that is what you observe here. So original level was here. Now when the squeezing action happens, the water goes out and this comes down, or the soil particles will be arranged in closer manner, and the voids are reduced. The voids which were occupied by the water, now they are reduced because the water itself has gone out. Because of that, you find there is some kind of settlement, right? So this process of, under a huge static load on saturated soil, the water goes out and the volume reduces. This whole process is known as consolidation. Okay, the volume decrease of soil under stress might be conceivably attributed to, what are the reasons? The reasons are, maybe when the load comes, the settlement occurs. The settlement occurs because of what all reason? The reason may be compression of the solid grains, compression of pore water, expulsion of pore water or pore air from the voids, thus decreasing the voids ratio or porosity. But what happens is, the first two are not the reason, because compression of the solid particles is negligible. Compression of pore water is also negligible. And then air, it may be compressed, but we are considering saturated soil. There is no point in talking about air. Air is not involved. The basic assumption in case of discussion of consolidation, we assume there are no air voids. So in geotechnical engineering practice, the solid grains as well as pore water may be considered as, incompressible. May be considered incompressible. Because of that, there is no question of this or this. Now it is only because of expulsion of pore water there will be compression, or this settlement is only because of expulsion of water. So thus compression of pore air and expulsion of pore water are the primary sources of volume decrease of soil mass subjected to stresses. Now again, air we are not considering because we are considering saturated soil. So overall, it is the settlement or decreasing volume is because of only expulsion of water. Okay. Now the process of gradual compression due to the expulsion of pore water under steady pressure is referred to as consolidation. That would be a nice definition, right? Okay. Now the process of gradual compression due to expulsion of water under steady pressure is referred to as consolidation, and this is a time dependent phenomenon, especially in clays. Okay, so most important thing is time is coming into picture. It is not just the stress or strain, and it happens in clays. This is what you should remember. Okay, now one more picture to depict the same thing. Right here there is a saturated soil. You can see that there is no air voids, and then when the water is put, there will be some pressure, and because of that the water goes out, and then the soil particles will be getting arranged in a more compact manner. There is a decrease in volume, and this decrease in volume leads to what is known as settlement, end of the settlement. In the process of settlement is inside. So original level, if you observe, it is here, it has come down. Now even this level has come down, so this is the final settlement. So as long as there is some kind of pressure developed inside this pore water, it tries to go out, and then if that pressure is reduced to zero, there is no question of water going out. Now as you see here, when you put the load, there is pressure which is developed inside the water, it is trying to go out. By the time it comes up to this level, there is no pressure left inside the water. Because of that, there is no need of further expulsion of water. There it stops. So we say that it is completely consolidated, right? As long as pore water pressure is present, it is trying to go out. Consolidation process is happening, and when water water under pressure goes out, and then the pressure of the water inside the voids is reduced to zero, we say that it is end of consolidation. Okay, the volume change behavior has two distinct aspects. First, the magnitude of the volume change leading to certain total compression or settlement. First one, right? And then the second one is the time required for the volume change to occur under particular stress. Means when you put the load, there is, as I told you, it is a soil is clay soil, it will be taking a lot of time. Now how much is that time required for the settlement, and what is the kind of settlement, amount of settlement that is happening, whether it is in few millimeters or few centimeters, what it is, right? That is what the point of consideration. Okay. Now in sands, consolidation may be instant. Yeah, in sands, as I told you, right? So because the permeability is quite large, instantly the water under pressure goes out without any difficulty. So whatever settlement that has to happen happens quickly in case of sands, but while in clays the process of consolidation proceeds for long time and thus needs greater attention. So that is what is the whole chapter is about, consolidation, right? So nowhere we are considering sands in case of consolidation. Whenever we say consolidation, it is obviously clays, and that too saturated clays. So Terziki's one-dimensional consolidation theory and assumptions. What is one-dimensional? What are the assumptions, and then theory? Okay, here there are assumptions. Now one by one we'll go through. The soil medium is completely saturated. This is the first assumption. In earlier slides also I have told that will not be having any case where the voids are filled up with air. No, voids are completely filled up with water. Because of that it is saturated. That is what is the assumption. The soil medium is isotropic and homogeneous, means the property of the soil everywhere remains the same. In every direction it is remaining the same. Everywhere it is homogeneous, in every direction it is isotropic. Means suppose if you got a soil layer, and then if you consider at particular point some soil, right? So if you take permeability in this direction, they may be different, right? But we are assuming that they are same, isotropic. In all the directions the properties are same. Now if you take a point A over here and then point B somewhere there, and if properties are same, then we say that it is homogeneous. So properties in all the directions are same, properties everywhere are same. That is what is homogeneous. Now Darcy's law is valid for flow of water. What is Darcy's law? We know that it is V is proportional to the velocity of flow is proportional to hydraulic gradient IH by L. So this particular property, law is valid or applicable. That is what is the third assumption. Now flow is one dimensional in vertical direction. This is what is one dimensional in the sense, now suppose this is the solid layer we are talking about, and we have to confine it within some boundary vertically, and when you put the load, maybe a building load or any other load, right? So when you put the load, whatever water that is present inside the voids will have to go either out upwards or it has to go downwards, right? So there is no question of water going sideways. Water is moving only in z direction, right? The load is coming vertically downwards. So this is what is one dimensional consolidation. You have got a confinement on the sides, and then the water is moving only in vertical direction. So flow is one dimensional in vertical direction. The coefficient of permeability is constant. I have told you properties are same, or V is equal to Ki. K is coefficient of permeability. It is same in all the directions and everywhere. The coefficient of volume compressibility is constant. What is this? We'll see in next videos. It is represented by a lowercase letter m with a suffix v. It's a some term, right, which is known as coefficient of volume compressibility, and this we are assuming it to be constant. The increase in stress on the compressible soil deposit is constant, in the sense when we put the load, right, we put the load, and then not that we go on putting the load. You put the load of a particular magnitude and then leave it for some time. The increase in the stress on the compressible soil deposit is constant, and generally this increase in the load or increase in the stress will be denoting it as delta sigma, right? Sigma is the stress, but delta sigma is not the additional pressure, which is additional stress which is put on the soil so that it gets squeezed or consolidated. The soil particles and water are incompressible. Fine, that's okay. Now these are the assumptions. Now what are the limitations? Now what are the limitations? Limitations are one-dimensional theory is based on the following hypothesis. Okay, limitations I have not told here. Next slide I will be talking about. Here one hypothesis that we'll be discussing. The change in volume of the soil is equal to the volume of pore water expelled. Obviously, the settlement happens only because of expulsion of water. So whatever volume change is there, that will be because of pore water expulsion. The volume of pore water expelled is equal to the change in volume of the voids. Obvious, but we are defining it as a statement. Since compression is in one direction, the change in volume is equal to change in height. This is more important, right? We'll be using it, of course, in a bit later stage, but I'll come back and then refer to this. volume changes because of the height change, right? So here if you talk about this soil layer, so whatever volume change is there, because of that height will be changed. The increase in vertical stress at any depth is equal to the decrease in excess pore water pressure at that depth. So delta sigma will be equal to delta U. Okay, the increase in vertical stress at any depth is equal to the decrease in excess pore water pressure at that depth. Means in the beginning, suppose there is something like 5 Newton per meter square, 5 Newton per minute square is the stress induced in pore water, right? When that is completely removed or expelled, the water is expelled, that same 5 Newton per millimeter square will be going on to the soil particles. That is what it is. Okay. Okay, now limitations. Okay. What are the limitations? There are 3 of them. In the derivation of one-dimensional equation of permeability, this is derivation, it should be not deviation. Permeability K in z direction, in vertical direction, Kz, and the coefficient of permeability Mv are assumed to be constant, but this is assumption. But as consolidation progresses, means as the time passes, void spaces decrease, obvious, because volume is decreasing, because of that the void space decrease, and this results in decrease in permeability, obvious. And therefore permeability is not constant, and the coefficient of volume compressibility also changes with stress level. So therefore Cv is not constant and Mv is also not constant. Okay, so coefficient of volume change or volume compressibility is not constant, K is not constant, and coefficient of consolidation is not constant. Okay, next is the flow is assumed to be one-dimensional, but in reality flow is three-dimensional. In case of a laboratory experiment, we conduct a test by taking a soil, putting it in a ring, right? This is the section of a ring. So you will be having a metal ring in which the soil is placed, and then the load is put, and porous stones are provided on top and bottom so that the water goes out only in vertical direction. This is what is done in a laboratory. But in case of actual soil condition in field, you cannot dictate the terms like the water which should move only in vertical direction. It will be even in horizontal direction, or any convenient direction in which the water flows. So that is purely an assumption. The flow is assumed to be one-dimensional, but in reality the flow is in three-dimensional. The third one, the application of external load is assumed to be assumed to produce excess pore water pressure over the entire soil stratum, but in some cases the excess pore water pressure does not develop over the entire clay stratum. So when you put the load, the water that is present inside these pores will be developing some pressure. Here what is assumed is everywhere, whether it is on the top, mid level, bottom level, everywhere the pore water pressure remains the same. That is not true, practically speaking, right? So assumed to produce excess pore water pressure over the entire soil, but in some cases the excess pore water pressure does not develop at all. Means not only it is same, but it may not be developed in some areas, right? Okay, governing differential equation. We don't have proof for your scope of syllabus is defining only the equation. So this is what it is. This is Terzigi's one-dimensional consolidation equation. Dou u by dou t is equal to Cv into dou squared u by dou z squared. This describes the variation of excess pore water pressure. Excess pore water pressure. See, this u is representing pore water pressure, right? Excess pore water pressure with time and depth. So variation of pore water pressure with time, variation of pore water pressure with respect to z, the depth, right? So this is the coefficient of consolidation, Cv. So this equation relates pore water pressure u, the time and the depth. Dou u by dou t is equal to Cv into dou squared u by dou z squared. Now, what is the solution for this? Solution of one-dimensional consolidation, that is this equation. The solution of variation of excess pore water pressure with depth and time can be obtained for various initial conditions. Now, what are the initial conditions? Okay, we'll stop here. We'll discuss these things in the next class. We'll stop.